So our last skill in our second learning unit here is on classifying and quantifying matter. So when we think about classifying matter, we just have a bunch of definitions that we want to make sure that we understand really well. And this is a great little infographic here, a little organizational chart that helps us put all of this together. So to help with the understanding of this, I'm going to tell you a story, and I'm going to kind of tell it a little bit more slowly so we can get all the pieces in. We can define anything with mass and volume as matter. So that represents kind of this gray area out here. Anything that has mass and volume we can define as matter. Now again, that matter could exist in solid, liquid, or gas forms, and we've talked about phases and phase changes already a little bit. But at its simplest, we're going to think about matter being comprised of atoms, right? And we know that atoms themselves are actually subdivided into subatomic particles, which are protons, neutrons, and electrons. So again, at its simplest form, we've got matter being comprised of atoms. So again, atoms being comprised of protons, neutrons, and electrons, which we've learned about in a previous skill. So all of these atoms comprise individual elements, right? And those elements are organized on a periodic table. So these elements are going to undergo chemical changes with other elements that are going to allow them to form compounds. So again, elements are going to undergo chemical changes, which means we're changing the chemical identity, and they're going to form compounds. The two main kinds of compounds that we focused on are ionic and covalent compounds. We've talked about in previous skills which kinds of elements would combine to form ionic versus covalent compounds, and again, how that happens. So what's unique about these substances is that they are going to have a fixed composition throughout. So whether they're the ionic compounds or these covalent compounds, they are going to have a fixed composition throughout. But we can take and mix these compounds together, and again, mixing is going to be a physical change. It's going to be often a reversible process. It might not be easy to do, but we're not chemically changing the identity of these species, but we're combining them together to form mixtures. So again, these compounds, right, which are different substances, can be combined together. That combination is going to be a physical change to create two different kinds of mixtures. We have homogeneous mixtures, where the composition of the mixture would be the same throughout, or heterogeneous mixtures, where it's different sort of throughout. So again, by definition here, homogeneous mixtures are going to have no visible parts. We're actually mixing it thoroughly all together. You can't tell one thing from another. Versus heterogeneous mixtures, where we've got visible parts. And we can actually think about maybe some rock formations as being great heterogeneous mixtures, where we're going to have different substances that we kind of mix there. Or again, if you imagined mixing together some copper pennies with some salt, right? We would mix them together, we could still easily see and pick out the copper pennies from the salt. So lots of different examples here, but it's really important to be able to understand these different terms and use these terms as a way to describe matter. A couple of other little things here to wrap up our chapter is how we think about quantifying matter. So we're going to talk about how we can determine molecular mass or molecular weight, which is going to be the sum of atomic masses. This is going to be relevant when we're talking about molecular compounds, which are going to be our covalent compounds. So I'm going to run through a couple of examples here to help us think about this. One thing that's going to be really important to have, and I will make a copy of this available online. I'm going to show you guys periodic table here, right? Now, if you have one that you want to bring with you, that's okay. I'm going to make this one available. I will ask to look at your periodic table if you have one that you'd like to bring in yourself, if you want to use it during quizzes and so forth. I don't want to have one that has too much information. So if it has one that has more information than I might allow, I probably will ask you to bring a copy of the one that I feel is appropriate here. So we're going to go through two examples here. The first is calculating molecular mass, and we're going to go through our table sugar and table salt examples that we've actually already used throughout this second unit here. So here is the molecular formula for table sugar, so sucrose, so it's C12 H22O11. So if we want to figure out what the molecular mass of one molecule of table sugar is, we are just going to add up all of the individual element masses. We have to make sure we take into account any subscripts, which tell us the number of those atoms. So I'm going to have 12 copper atoms, and I can look on the periodic table to see that one copper atom is 12.01 atomic mass units. I have 22 hydrogen atoms. The atomic mass of one hydrogen atom is 1.008 atomic mass units. And then I have 11 oxygen atoms, and each oxygen atom is 16 atomic mass units. Now again, if you've taken a chemistry course before, you might be thinking, well, wait a minute, what about the whole grams per mole units? We're going to get to that in our next chapter, but because we really haven't talked about the mole yet, we're not going to be using those units yet. We, in this learning unit, we're really just talking about atoms and ions, and so since we're talking about specifically atoms, we're going to have atomic mass units. Go through the math here and multiply this through. You get 342.296. That's what my calculator tells me. When we do significant figures, when we're adding things together, I need to look at the number of digits to the right of the decimal place. I've got 2, 3, and 2 there, so I'm limited by the fewest number of significant digits to the right of the decimal place, which means I have to limit this to 2 significant figures to the right of the decimal place. So rounding this takes me to 342.30, and my units for this are going to be atomic mass units. So this would be the molecular weight, which we use for a molecule, which is again a covalent compound. All right, for ionic compounds, we use a slightly different term. We call it formula mass, since ionic compounds are not really molecules, so it's a little bit just of terminology and semantics, but we handle this the same way. So let's take our table salt. Table salt is NaCl. So I'm going to go and I'm going to look on the periodic table, and I'm going to look up for sodium. I've got 1 sodium, and that's at 22.99 atomic mass units. And then I've got 1 chlorine atom, and that's going to be 35.45 atomic mass units. Go ahead and add those up, and the formula weight or formula mass for table salt is 58.44 atomic mass units. So again, just to highlight, once we get to further chapters, we'll use the units of grams per mole if that's something that you're familiar with, but just because we haven't introduced the mole until our next learning unit, we don't use those units yet. But you ultimately determine these the same way. You add up the numbers from the periodic table to give you the overall weight. All right, the last little thing here is just telling you about some chemical history and some important properties that have allowed scientists to do the work that they've done over the past couple of centuries. But these are going to represent little mathematical tools that we'll use for some future problems. So the first is a law called the law of mass conservation. It says that the total mass of substances present does not change during a chemical reaction. Well, what does that mean in English? Basically, you can't make something from nothing, and stuff doesn't just disappear. So how we could use that is we could actually determine the mass of an unknown single reactant when we know the others. So let's see if this makes sense with just a very simple example. Let's say we react A plus B plus C together, and they all combine to make D. Now I'm not concerned with whatever the chemistry might be, but if we started with 25 grams of A and 25 grams of B, and we ended up with 100 grams of D, we know then that the mass of C must be 50 grams. We can't lose matter and we can't create matter. Okay, we're just exchanging sort of how it's all sort of divided up between 3 different substances or all kind of together in one substance. So we're going to be able to use this from time to time in problems in the future, that we can just do a little algebra, if you will, to solve for this unknown. Thinking about this last problem here, same kind of a thing. One of these laws is called the law of definite composition. So for a given compound that's composed of the same elements and the same parts by mass, that's kind of the definition of definite composition. So what does this really mean? Tell me it in English. It means that basically every compound that is the same compound is going to have the same makeup. So we can use that to determine the mass of a single element in a compound if we are given something called percent composition. Now, what's really more important is understanding that if we're ever given something as a percent, there's no units with percent. So we need to be able to put something into a quantity that has units so that we can do all our tricks with unit conversion. So I want you to think about in every 100 as a way to get out of percents, which are unitless. All right, so as an example here, let's imagine that I tell you we have a compound that is 50% X, 25% Y, and then 25% Z. We can use this information to say, well, you know what, if that's the percent composition, if I had 100 grams, I could say in every 100 grams of my compound, I would have 50 grams of X, 25 grams of Y, and 25 grams of Z. Well, now I have something. I have a quantity that has units that I can do something with. Before, when it was just percents, I really didn't know how to start a unit conversion problem. But now that I have something with grams, I can probably move to another unit and move my solution to the problem forward. So that's our last skill for our second learning unit, and that wraps up everything we have here.